Hey everybody, this is our video solution to problem 4 from quiz 5. Here we're back to computing Laplace transforms. We get to use the table, and this is all about using the first shifting theorem, which is precisely this line in the table. All right? So you notice these exponential functions are popping up all over the place. All right? And that's because we have this very special theorem says if you take the Laplace transform of a function multiplied by an exponential, all you have to do is take the Laplace transform of the original function f. So that's what this big F means, right? So big F of s would be the Laplace transform of f. So you just take that Laplace transform, but then once you get the answer, right, here's my Laplace transform as a function of s, you want to apply a shift, right? You're going to replace s by s minus a. All right, so we have this Laplace transform of a sum of functions. We know we can break up the Laplace transform and even pull coefficients out because the Laplace transform is linear. So the Laplace transform of, and we'll just copy here, 4t squared e to the 3t plus cosine of negative 4t e to the 4t, whoops, no parentheses there, minus, okay, now that's kind of weird. There's a derivative of some function times e to the 2t. Okay, we can break this up as 4 times the Laplace transform of t squared e to the 3t plus the Laplace transform cosine of negative 4t e to the 4t minus the Laplace transform of the derivative of f times e to the 2t. So let's take these one at a time. So first, I'm going to copy the 4. And what I have here is a function t squared multiplied by an exponential. So I'm using the first shifting theorem. Okay, so FIST here. And in fact, I'm going to use it in all 3 of these Laplace transforms. So that tells me if I want to compute the Laplace transform of t squared times an exponential, I forget the exponential. And I just compute the Laplace transform of this f, right, which in this case is t squared. Okay, so to get the Laplace transform of t squared, I'm going to use this top line. This will end up giving me, so in this case, my n is 2. So I get 2 factorial, which is 2, over s to the 2 plus 1. So that's going to be s cubed. All right. Now, I'm making a little space here. Why am I leaving all that space between my s and my 3? It's because we are using the first shifting theorem. There is an exponential, right? We can't completely forget about it. But all that exponential is going to do is shift my Laplace transform by, well, whatever this a is. So in this case, my a is 3. So I'm going to have to do a shift, replace my s by s minus 3. Okay. So I get 4 times 2 over s minus 3 quantity cubed. Okay. Note, this is not the same thing. Right? This is not equal to 2 over s cubed minus 3. You don't take the s cubed and then shift the output of s cubed. Right? You have to take the entire function and shift every s, right? Not s cubed, but s, right? You have to shift that by 3. Okay, so this is that correct answer. Okay, so plus, now we want to do the Laplace transform. Well, again, we have a function times an exponential. So we're using the first shifting theorem. Okay, we're using this. So all we need to do is compute the Laplace transform of cosine of negative 4t, and then shift all my s's, in this case, by 4. So the Laplace transform of cosine of something times t, so in this case, what's my something, right? Now, we have to be very careful. Both of these formulas use the letter a. But they're not the same a, right? Because they're coming from different formulas. Okay, here my a is negative 4. Here my a is positive 4. They're not the same a's, right? We have to distinguish between them. Okay, so let's see. For cosine, I use s over s squared plus a squared. So in this case, my a is negative 4. So negative 4 squared is 16. Okay, but this isn't right because I have to use the first shifting theorem and I have to shift. How much by? Well, minus 4. So s minus 4, and then this s squared becomes s minus 4 squared. All right, make a little extra room. Okay, so we'll replace all my s's with s minus 4s. All right, we go to the last one. Minus. Okay, now this is tricky. It says here, I need to take the Laplace transform of a derivative and then times e to the 2t. So again, it looks like a first shifting theorem, only instead of f, I have f prime. Well, what can I do? Well, I do have a formula for the Laplace transform of a derivative. Okay, fine. So let's just write that down. So I'm going to have minus, okay, let's use a parenthesis. I have s, and we'll leave a little space. The Laplace transform of f, right? It's not a y here. It's actually an f, minus, and then it would be, well, y of 0. Well, now my y is f. So this would be f of 0. Okay, now why did I leave all this space? Well, remember, there's this exponential here, and I have to use the first shifting theorem. So instead of an s, I get an s minus, in this case, a 2. So I have s minus 2 times L of f minus f of 0. All right, and of course, I could distribute this minus and blah, 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 maybe add stuff together, but I don't want to do that. That feels bad. Okay, now we're not quite done with the problem, though, because there's this last line, which says, be sure to state for which values of s the Laplace transform exists. All right, so let's do this one by one again. We head back to this first bit. Let me ditch this bit. So let's see. Originally, we were just looking at t squared. Okay, we forgot the exponential, and we know that Laplace transform is defined when s is greater than 0. All right, but when you hit it with this exponential, it shifts it over, right? S is going to have to be bigger than a, where a here is whatever is this exponent, right, in the exponential. So in that case, it's a 3. So for this piece, we would need s greater than 3. When we head over to this next Laplace transform, okay, the cosine, that doesn't give us anything new. It just has to be greater than 0. But again, this exponential has a 4 in it, so this part is only going to be defined when s is greater than 4. All right. And what about for the last part? Well, it's not stated here in the table, but we have this extra piece of information. We know that f prime, let's see, is a piecewise continuous function, and f has exponential order 3. So something about the first shifting theorem tells us what to do. The first shifting theorem tells us we need our s in this situation to be greater than the sum of the exponential order of f, so in that case that's 3, plus, right here, this exponent on for e, so we need it to be greater than, in this case, 5. So if we want this Laplace transform for the entire function to exist, well, we need s to be greater than 3, greater than 4, and greater than 5. Well, okay, the strongest of those conditions, right, is it has to be greater than 5. Okay, so the Laplace transform exists when s is greater than 5. Okay, this is like the intersection of all these domains, right? Because if you just knew it was greater than 3, like say it was 3.8, well, neither of these two is going to exist because 3.8 isn't greater than 4 or greater than 5.